have liftoff of the Space Shuttle Columbia, continuing space research through tether satellite technology.
On February 25, 1996, NASA and Italian researchers made a bold attempt to harness the power in the atmosphere. They generated electricity with a satellite on a wire.
Good work. Let's make sure we stay that way. Understand.
The mission was part of a new experiment of tethering satellites in space.
Attitude verification. 3-14.
The experiment was based on the simple principle that when you move a conductor through a magnetic field, electrons start to flow. This generates an electrical current that can flow through a circuit. The satellite was thrust into space using small gas jets, and the 13-mile-long cable began to unreel.
If you put a wire inside of that tether, you now have a moving wire that moves across a magnetic field. That magnetic field, in this case, is Earth's magnetic field, and the motion is the motion of the space shuttle moving at very fast, high velocities, orbital speeds.
Lying down here, John.
The moving wire in the Earth's magnetic field generated 3,500 volts, enough energy to power a space station.
Okay, we see the tension go way down, but the tether's still going out fine. Very slight lateral oscillation.
The tether was clearly visible from the ground. It was one of the biggest man-made objects ever sent into space. For 5 hours, the tether swept through our planet's magnetic field, generating more and more electricity.
Copy.
The wire was generating so much electricity that a spark jumped from the wire to the satellite deployment system and burned through the tether. NASA will try the experiment again because it could lead to a new, more reliable power system for space stations and help avoid situations like the Mir mishap.
We're moving to actually is if we drive current in the opposite direction in the tether and we can force the current to go the other way, it becomes a propulsive device. So a propellantless spacecraft, the next generation of space travelers may be using electric propulsion devices as opposed to chemical propulsion devices. A little Star Trek, if you will.
So how did NASA manage to generate current electricity in space? Well, then they did literally, they just got a piece of wire, about a mile in length, and then they dragged it across the Earth's magnetic field. How would that generate current? So that's one of the things that we will get to discuss.
It's just, it's no big thing. How are we going to do it? Okay, fine, we'll do it. Oh, Mama. Are you okay? I'm gonna lose that nail.
Kramer from Seinfeld.
It's just...
Michael Richards. Amazing acting. Beautiful setup. This is what happens in commercial buildings. Usually, if you come in contact with the current from outside, just like he did, what's going to happen is the circuit breaker is going to kick in, and then it's going to shut off the electricity. So the question is this: how does this circuit breaker know that you're doing something stupid? How does it know that you just got in contact with the current somehow and be able to actually shut off the electricity? All right, so Faraday's Law is what we've been discussing. So last time we've done it conceptually. That was like at the art school level. And today we'll do it at the college physics level. So there's going to be a little bit of math, not too much, but a little. So what do we know? We know that the Earth stat discovers that the current causes magnetism, right? So if there's current, there's going to be magnetism. So the question is, given the fact that we get current, the magnetism out of current, is it possible that we can also generate current using magnets? So the answer happens to be yes, except there's a bit of a trick involved. What you need to do is you need to have a loop of wire. Just not a wire, but a loop of wire. And then you have to have a magnet. And what you need to do is you need to vary the strength of the magnetic field inside the loop by moving the magnet back and forth. And then what happens is the current is going to go one way when you push the magnet in the forward direction, and then the current reverses direction. So what's happening is the direction of the currents is alternating. So this is known as the alternating current. And the only way you're going to be able to generate this current is by varying the strength of the magnetic field intercepted by the loop or within the loop itself. There are a couple of ways you could do it. Either you can move the magnet back and forth, or you can change the area of the loop which is exposed to the magnetic field. So you can change the size of the area of the loop which is exposed to the magnetic field. So those are the two ways that we could do this. All right, so we got the summary statement. All right, guys, delta becomes D. This is more of a calculus explanation of the same thing. I end up using this one because this one is clearer. So if you vary the strength of the magnetic field inside the loop, area of the loop, it's going to induce current. That's one way of doing it. There's a second way of doing it, is keep the magnetic field constant, and then change the size of the area exposed to the magnetic field. So D means change. It's the same as delta in essence. All right, so how do you change the size of the area exposed to the magnetic field? It's simple. The only thing you have to do is just spin it. So there are two ways you can induce current. Number one, vary the strength of the magnetic field inside the loop, it's going to induce current. And there's a second way of doing it. Just keep the magnetic field the same and then just change the size of the area exposed to the magnetic field. So instead of saying that, hey, you can generate it two ways, we could just come up with one single statement. The statement that we're going to end up using is this statement of flux. Flux means flow, just like before. This time what's flowing is the magnetism through the area of the loop. That's it. So flux represents the amount of magnetic field which is going to be intercepted by the area of this loop. So if you vary the flux, that induces current. That's the meaning of that statement. So how do you vary the flux? Well, it's easy. You're looking at it. You can either vary the strength of the magnetic field intercepted by this area, or you can keep the magnetic field constant just like that and vary the size of the area exposed to the magnetic field. That's it. So those are two ways of actually changing flux. All right, so there's a statement here that I need to focus on, this statement. All right, so this is the one that we need to focus on. All right, notice that change of flux, in essence, is going to generate an electromotive force. That's the voltage. And the voltage is what's going to drive current, right? So change of flux induces voltage. Voltage is what drives current, except there's a negative sign. All right, so what's the meaning of the negative sign? The meaning of the negative sign is related to the direction of the current. All right, so it's going to give us the direction of the current. And simply put, and this is the stuff that I'm about to emphasize and overemphasize. If you look at the equation tells you what it does. All right, so as it so happens, electromotive force and the current is going to point in a direction that's going to oppose any change in flux. That's the reason why you end up placing it in front of change in flux. That's what it means. So the current is going to point in a direction that's going to oppose any change in flux. That becomes the Lenz's law. All right, so Faraday comes up with his own law, 1830. And about 2 years later, this guy, Lenz, he was able to answer the question, why is the current moving in the direction that it does? It just so happens the current moved in a direction which is kind of unexpected. And the Lenz's explanation is this. This is kind of weird. This requires a bit of paying attention to because you can't really figure this out by reading a book. This is a visual thing. So, simply put, the current is going to move in a direction that's going to oppose any change in flux. That's what it means. All right, that's what it says. But what does it mean? Let's focus on that one. All right, so notice that you got this magnet, pyromagnet, and then we're moving this magnet in the forward direction. When you're moving it in the forward direction, the intensity of the magnetic field intercepted by this area is going to change. It's going to increase, in essence. And then the current is going to move in a direction that's going to oppose that increase. All right, so which means that the circuit needs to generate its own magnetic field, opposing this change. So the induced magnetic field is going to be pointing in the opposite direction. All right, so as you're moving the pyromagnet in the forward direction, as you're increasing the strength of the magnetic field within the loop, the induced current is going to move in such a direction that the induced magnetic field is going to oppose that change. Notice that the induced magnetic field lines are pointing in the opposite direction. All right, so that's one way of looking at it. So I'm just going to attack this concept from multiple perspectives because explaining that way, though works, it barely works. All right, so which means that we have to give you multiple choices here, so you have a better understanding of it. Another explanation, and this one is going to be clearer, is this one. All right, so I'm representing a three-dimensional system, two-dimensional, right? And notice that you saw the dots, which means that the magnetic field lines are coming out of the page. And what I'm doing in essence is I'm increasing the amount of magnetism intercepted by this area. All right, so this is a magnetic field line coming out of the page. As soon as initially there was no magnetism, and all of a sudden, boom, there's just one line coming out of this page, right? So what will the circuit do? The circuit is not going to like the fact that you're varying the strength of the magnetic field here. So it's going to induce its own magnetic field opposing that change. So as soon as there's a line coming out of the page, it's going to induce a current inside the circuit. And the magnetic field generated by that current is going to oppose that change. So here's the original magnetic field, and here's the induced magnetic field. The induced magnetic field is opposing it. It's in the opposite direction. So which direction does the current need to move in order to generate this induced magnetic field? So using the right-hand rule, number one, number two, more like that, you know that the current needs to move in the clockwise direction in order to generate an induced magnetic field that's going to oppose that change. That's it. So if you increase the strength of the magnetic field coming out of the page, the current is going to move in a direction which is going to oppose that change in magnetism. It's going to move in a direction which is going to oppose any variation of the flux in essence. All right, so in this case, magnetic field is coming out of the page. The induced magnetic field has to oppose it in the opposite direction. In order to generate this induced magnetic field, the current needs to move in the clockwise direction. That's it. All right, so let's reverse the scenario. What if I'm reducing the strength of this magnetic field? All right, so that's what I'm trying to signify, which means that whatever the magnet is on the other side of the page, I'm pulling it away. As a result, what's happening is the strength of the magnetism being intercepted by this area is diminishing. So under the circumstances, induced magnetic field is going to be coming out of the page. I'm diminishing the value of the magnetic field. So in this case, the induced magnetic field is going to oppose that change by coming out of the page. So which means that the current is going to reverse itself. So the current is going to move in a direction that's going to oppose any change in flux. In this case, I'm changing flux by changing the strength of the magnetic field inside the loop, and then the current is going to keep moving in a direction that's going to oppose that change, and that's it. All right, so that becomes the lines as well. All right, so we got a few more visuals here. So I'm varying the strength of the magnetic field inside the loop. I'm using delta this time. I'm increasing it this time. So which means that the strength of the magnetic field intercepted by this loop is increasing. So what should happen? The current needs to move in a direction that's going to oppose that change. Which direction will the induced magnetic field be pointing in order to oppose that change? It needs to be pointing in the opposite direction of the original magnetic field. So which means that the current needs to move in this direction in order to generate a magnetic field going into the loop in that direction. All right, so if I'm increasing the strength of the magnetic field through the loop, what needs to happen is the induced current needs to move in this direction so that the induced magnetic field can oppose that change. In this case, I'm reducing the strength of the magnetic field being intercepted by the loop. If that's the case, the current needs to go in the opposite direction to oppose that change. So which means that the induced magnetic field needs to move in that direction. So which means that the current needs to move in the opposite direction. So that's it, guys. That's the meaning of the lines of law. It's going to move in a direction that's going to oppose any variation of the magnetic flux. It's going to move in a direction that's going to oppose any change in the strength of the magnetic field within the loop. That's what it means to translate it. So the direction of the current can be determined by the direction the current needs to move in order to oppose any variation of the strength of the magnetic field generated by an external source. I case in point, you have some kind of a metal ring, and then you just drop it through an external magnetic field. So there's a region of custom magnetic field. The magnetic field within this region is pointing into the page. And then is the ring following, notice that there's no current here. There's no current here, no current here, there's current here.
Professor, your mic is messing up.
All right, cool. Let's try this. Is it better?
Yes, sir.
Awesome. Give yourself 5 points for the feedback. All right, so there's current, there's current. Current is going this way, current going the opposite direction. All right, why is there a current here, no current here, and there's current here? It's obvious that there won't be any currents here because there's no magnetism being intercepted by the loop, right? Here, notice that what's happening is we're increasing the strength of the magnetic field intercepted by this area, right? So the current is going to move in a direction that's going to oppose that change. Here, we are diminishing, reducing the strength of the magnetic field. Once again, the current is going to move in a direction that's going to oppose that change. Here, there's no change in magnetism inside the loop because it's a constant magnetic field region, right? So if there's a variation within the strength of the magnetic field intercepted by the loop, there's current. Once again, if you vary the strength of the magnetic field intercepted by the loop, there's current. You're increasing the strength of the magnetic field, the current goes this way. You're reducing the strength of the magnetic field within the loop, the current goes the other way. Got a lot of applications.
Not only can electromagnetic induction stop a piece of metal, it can get one going again, because a piece of metal doesn't like to be in a region of strong changing magnetic field, which I have right here. If I take this ring of aluminum and put it down in the field and turn it on, you should actually be able to see the aluminum jump when I turn the field on. You ready for this? Here it goes. Watch. There.
All right, this one is
Not only can
interesting.
electromagnetic induction,
because he's got an aluminum ring. And he's able to get the aluminum ring to jump. The thing about the aluminum ring is aluminum is not magnetizable. You cannot magnetize aluminum. You cannot magnetize gold. If you have any sort of ring, metallic ring, whether it's magnetizable or not, it makes no difference whatsoever. You can get it to jump. So the question is how? Well, it's a metal ring, obviously. So what happens is it's got an electromagnet right in the middle. As soon as he turns on the electromagnet, he's able to vary the strength of the magnetic field intercepted by this area, right? So he's increasing the strength of the magnetic field intercepted by this area. And then the induced current, and there's going to be an induced current inside the metal, goes in a direction which is going to oppose that change. So which means that the induced current is going to move in a direction just so that the induced magnetic field is going to point in the opposite direction of the external magnetic field. All right, so these magnetic fields, because they're in opposite directions, they will repel. All right, so this is an example. It's an example of the Lenz's law. So that's what's happening in essence. All right, so he's varying the strength of the magnetic field. He's varying the amount of magnetic field within the loop itself. And then the current is moving in a direction which in order to oppose that change in magnetism. So the induced magnetic field is going to be pointing in the opposite direction of the external magnetic field. And when the magnetic fields are opposing each other, it causes that repulsion that we just saw. All right, so the next question is, what if this ring had a gap in it? All right, would we still be able to generate the same effect? What if there was a gap? What if there was a gap right there? All right, if there's a gap, you know, the current is not going to be able to form because of the gap right there, right? If the current doesn't form, do you think it's still going to be able to jump? All right, so it's the same demo. This time, notice that there's a gap right there. So induced current is going to move in a direction that opposes any change, right? But the current needs to have a path, a complete path, or else the current is not going to form. If the current does not form, if the current doesn't form, obviously there's not going to be an opposing magnetic field. So the experiment didn't work out.
This is Lenz's law kit. It demonstrates very nicely how magnets behave when they fall down metal tubes. We have a slug of metal here. We're going to drop it down the tube, and there's a nice window in the tube, so you can see all the way down. Boom, down she goes. Turn it down, up, and still go down at good speed. It's called gravity. Well, now, if we were to make a magic pass, drop it down again, something else might happen. Look at that. Extraordinarily slowly. And the other way up. Oh my, oh my, oh my. Well, of course, it's a slip.
All right, so the question becomes, when you drop a magnet, why does it slow down?
Extraordinarily slowly.
This is an aluminum tube. It could be a copper tube, aluminum tube. In this case, it's a copper tube. Copper, just like aluminum. It's not something that you can magnetize. So, given the fact that the copper does not become magnetized, how is it that it's able to slow down a magnet falling through the tube? Once again, what's happening is when you drop the magnet within the loop, it's moving in the downward direction. As it's moving in the downward direction, and the entire tube is going to act like a loop of wire, except it's got many turns, obviously. And when you start changing the strength of the magnetic field within the area of the tube, what's happening? It generates eddy currents. It's called eddy currents because there's that surface currents that you're looking at. All right, so the surface currents, the eddy currents, will move in a direction. That's going to oppose that change. So, which means that the induced magnetic field is going to be pointing in the opposite direction of the incoming magnetic field. As a result, obviously, the motion of the magnet is going to slow down.
And the other way up. Oh my, oh my, oh my. Well, of course, it's a sleight of hand. This is highly magnetized, and this little buddy I showed at the beginning is not magnetized at all. The highly magnetized one is creating a little eddy current in the tube, which itself creates a little magnetic field that opposes the descending slug of metal. And it's trying to stop it going down. It's a nice demonstration of it, too. Lenz's law kit.
All right, so let's do a fast review of this thing. All right, so we've been discussing the Lenz's law, right? So the Lenz's law is getting introduced a negative sign into the formula that we've been using. So any variation of flux will induce electromotive force. Electromotive force is what drives current. Electromotive force is the same as voltage. We discussed that. All right. So we can vary the strength, the value of the electromotive force by increasing the number of turns. So you increase the number of turns, the voltage goes up, the current goes up. You reduce the number of turns, the voltage goes down, the current is going to go down, obviously. Now the direction of that current, the induced current, is going to be determined by the Lenz's law. Simply put, the electromotive force is going to point in a direction, or the induced current is going to point in a direction that's going to oppose any variation of the strength of the flux that you're looking at, any variation of flux, in essence. So what purpose does the Lenz's law serve? The purpose of the Lenz's law is to figure out the direction of the induced current. That's it. All right, so here's a conceptual problem here. So we have a loop which is placed parallel to this piece of paper. Now what we're doing is we're increasing the strength of the magnetic field intercepted by this loop. Assume that the magnetic field is pointing out of a page right, so here's what's happening. I'm increasing the strength of the magnetic field, pointing out of this page. So which direction should the current move, induced current move, in order to prevent the change? All right, so given the fact that the strength of the magnetic field coming out of this page is increasing now, we've got 4 magnetic field lines being intercepted. All right, so these are coming out of the page. The 5th one is just started to increase, so this is a new one. So the induced current has to move in a direction that's going to oppose that change, right? So the induced magnetic field needs to point in the opposite direction into the page in order to prevent this change. So which means that the induced current has to move in the clockwise direction. All right, so the induced current needs to move in the clockwise direction.
It's just, it's no big. How are we going to do it?
How does a circuit breaker know that someone from outside accidentally interrupted the circuit? All right, so take all the time you need to study this carefully. I'll give you guys like 10 more seconds. All right, so the circuit breaker is a simple design. You got your AC generator, which means that the current is moving this way and that way. All right, so the green is pointing in the opposite direction of red. That means that it's an oscillating circuit. It's an alternating current circuit. It's just going this way and that way. And then we have the ground fault interrupter, which is known as the circuit breaker right there. Boom. The entire thing is going to have a circuit breaker within it. All right, so circuit breaker is going to be hooked onto a sensing coil. Sensing coil has an iron ring within it. It's a cute little setup. There's an iron ring because iron is very easily magnetizable, so it's going to be able to contain the magnetic field within it. All right, so you got to remember that the current is going this way and that way. It goes this way and that way at the same time. You got the current going this way, you got the current going in that way. So this current is going to be changing in value, and this current is going to be changing in value as well as the direction. It keeps reversing itself. All right, so the net current intercepted by this coil is going to be 0 at all times. If there's no interruption, the net current, not the net current, the net magnetic field intercepted by this coil is going to be 0. All right, because current moving this way and that way, the red current is going to create a magnetic field going in this direction. The green current is going to generate a magnetic field going in the opposite direction. All right, looping in the opposite direction. So the total amount of magnetic field intercepted by the sensing coil is going to be constant in essence. So there's no change within the strength of the magnetic field inside the coil. If somebody comes from outside and then comes in contact with the current, this person is going to introduce a lot of resistance. So what happens to the current when there's resistance? The value of the current is going to change, right? Depending upon which wire you touch, green wire may have a current value which is significantly smaller than the red one. If that's the case, there's going to be a change of flux, magnetic flux, within the coil. As soon as there's a change in flux within the magnetic coil, within the coil itself, what happens? There's going to be current inside the sensing coil. It's going to activate the circuit breaker, and then it's going to shut itself off. So they end up using the Faraday's law and the Lenz's law in order to build these circuit breakers. All right, so the power generators work on the principle of Faraday's law. If you want to generate current, the only thing you have to do is just change the strength of the magnetic field within the loop. The way to do it is instead of varying the strength of the magnetic field within the loop itself, we end up changing the area, size of the area of the loop, which is exposed to the magnetic field. How do we do that? Basically, you just instead of constant magnetic field, it's down by mechanical means. All right, so the best answer to this question is mechanical energy gets converted into electrical energy.
To generate electric power using a lemon. When you do that, you get what's called direct current.
We've already seen this one. All right, so you get a loop of wire and you spin it 60 times per second.
It comes out on that oscilloscope, which is simply a device for showing the voltage.
You spin it 60 times per second inside a constant magnetic field. As a result, the current is going to keep changing direction 60 times per second.
Power, it will start going up and down like this. Okay, so when you see that going up and down, you know that we're generating electricity. And all I have to do to generate electricity is to turn on the water. All right, are you ready for this? You better get out your umbrellas in the first few rows. Here we go. And there it is, hydroelectric power. To generate. All
right, so he's spinning it 60 times per second. Notice that the voltage keeps changing direction. That's the voltmeter oscilloscope. And the voltage is what drives current, so the current is going to change direction. All right, so the only thing we have to do is spin this thing 60 times per second in a constant magnetic field. This setup is known as a power generator. All right, so again, an AC generator. The AC generator is also known as a turbine. All right, so an AC generator, you end up seeing this wiggly thing, which means that the current is going up and down. Its value is changing, which means that you keep reversing the direction of the current. All right, so we've got to do a little bit of math at this point. Let's get back to the notations. What's happening is you have this loop, and we are spinning this loop inside a constant magnetic field. Omega here, as you will remember from physics 1, it represents two things. It represents this rotational speed of the loop. Also, it represents the angular frequency. Frequency is the number of times, frequency represents the number of seconds per second. All right, so the number of times this thing is going to go around within a single second is known as frequency. And if you represent it in terms of angular frequency, meaning that it's rotational motion, it's the number of times it's going to spin within a single second. All right. In this case, we're trying to spin it 60 times per second. All right. So what's happening is by spinning it real fast, we end up changing the size of the area which is exposed to the magnetic field 60 times per second. So which means that we end up changing the flux 60 times per second. As a result, by varying the flux by spinning at 60 times per second, we're generating an electromotive force. And that's what we're doing. All right. I'm going to skip the mathematics for you guys because the emphasis is not going to be on derivations at this point. So I'm just going to go from here to there, and then I'm going to put the emphasis right there. All right. So any variation of flux through the loop, which has a number of turns, is going to induce an electromotive force. All right. And in essence, I'm changing the strength of the flux or the amount of, all right, so I'm varying the flux in this case. By varying the flux, I'm inducing an electromotive force. So the induced electromotive force is going to be represented by this formula. Okay, so what this means is when you vary the flux, electromotive force is going to go up and down in value. All right, so this represents the maximum value that the electromotive force is going to attain. And this is going to represent the maximum value it's going to attain in the negative direction. So which means that the value of the electromotive force is going to change up and down as a sine wave. All right, so electromotive force is going to increase in this direction, and then it becomes maximized. And then it changes direction, and now the electromotive force is going to reduce, and then it's going to become minimum, and then it's going to change direction, and then it's going to increase in this direction, it becomes maximized, and then reverses direction, and then it goes in the opposite direction, becomes maximized, it reverses direction, it goes in the opposite direction, and becomes maximized in time. All right, so this term that you're looking at, epsilon naught, represents the maximum value that it's going to have. This is known as the amplitude. These are the maximum values that it can have. It can have a positive amplitude as well as it can have a negative amplitude. So the individual value, electromotive force value is going to vary between these two values, maximum and the minimum in essence. All right, so that's the meaning of this equation. What that means is the electromotive force is going to increase and decrease, and then it's going to keep changing direction. So the value is going to change, the direction is going to change. All right. The maximum value that it can attain is going to be given by this formula. Okay, so you don't have this formula on the formula sheet, so you have to put it on your formula sheet because there will be a bunch of questions regarding this. So the maximum value that the electromotive force can attain is going to depend on NBA, that's your National Basketball Association, times omega. Omega tells you how fast you have to spin this thing. All right. So it depends on the number of turns that you have on the loop. It's going to depend on the strength of the magnetic field, which is going to be intercepted. That's going to be constant. It's going to depend on the area of the loop that's going to do the interception of the magnetic field. It also depends on how fast you spin this thing. So the faster this is spinning, larger the amplitude is going to be. Larger the number of turns, larger the amplitude is going to be. Stronger the magnetic field, larger the amplitude is going to be. Bigger the area, larger the amplitude is going to be. That's it. So this represents the maximum amplitude that the voltage can have. All right, so sine wave, cosine wave, in this case, it's a sine wave. Sine waves look like that. And this is the expression that we use for the sine wave on the x direction. The y is going to represent the amplitude. Notice that the amplitude is going to change depending upon where you are on the x-axis. And here, the amplitude is going to change depending upon where you are on the time axis. It's the same thing. So this is from Treg. It's the same concept. All right, so the amplitude, the electromotive force is going to change depending upon where you are on the time axis. Here, it's going to be maximum. It's going to be less than maximum. It's going to be less than the previous value, which means that the value of the electromotive force is going down. All right, once again, guys, put this on your formula sheet because it's not there. I've been meaning to put it on the formula sheet for years, except evidently never a priority at this point. All right, so moving forward. So this one is a derivation that I'm not interested in. Okay, so there's got to be something here that I'm interested in. All right, that's not for you guys. But this one is. All right, so the voltage is going up and down, right? So what does the voltage do? The voltage is going up in value, and then it's going down in value, and then going up in value. Every time the voltage does that, you notice that not only the direction of voltage is changing, as well as its value is changing. Same thing is going to happen to current. All right, so the voltage is going to go up and down. The voltage is what drives current. So the current does the same thing. The current follows the voltage. All right, so the voltage is what drives charges up and down, and then the current does the same thing. Notice that the voltage graph looks exactly the same as the current graph. More like, I should say, the current graph looks exactly like the voltage graph, in essence. Here's a question, though. Okay, it's got some practical implications. How much current do we get from a whenever we are paying, when you get the electric bill, for example? All right, so what are we paying for in essence? Because I'm looking at this. On average, I'm getting 0 voltage from the power company, and on average, I'm getting 0 current. All right, so notice that my current value is going up and down. All right, so I got the voltage. As soon as I have an appliance, the voltage is going to start driving current through the appliance. So I'm looking at it. I got the TV running in the background. I got a bunch of computers in front of me. I got other computer on the side for video editing purposes. And I got all these lights around me. Obviously, the voltage that I'm getting from the power company is being put to good use. I'm generating all this electricity, obviously. But at the same time, being a physicist, I know on average, I'm getting 0 electricity out of the power company. So the question is, what should I be paying for? What is it that I'm paying for? All right. I mean, these guys give me voltage and they take it away right away. All right. And likewise, they give me, I get current out of them, but they take it away right away. On average, I get nothing. On average, if I'm getting nothing, what is it that I'm paying for? And all of a sudden, that becomes contentious. All right, guys. It doesn't seem like it because the course is online and I'm behaving really well. I'm not a very politically correct person. All right, I can hurt the hell out of someone, emotionally or physically, just for the fun of it. Sometimes it's fun to do. I wouldn't do it with students, but if you're my colleague or my boss or something, now you have problems. All right, it would be fun in reality. Power companies, I think those guys are fair game, because they got engineers on all that stuff, and then I've been teaching engineering on the side as well as physics, and I know how well the engineers understand physics. It's usually not that good. Their understanding of physics is not very good, despite the fact that engineering is applied physics. They focus too much on math, they miss the points, and then they struggle as a result. It becomes really hard for them to get their engineering degrees towards the end because they don't realize that what they're dealing with is applied physics. And it's usually fun to call up the power company to complain. All right, this is one of my pranks. I enjoy pulling these kind of pranks on people. I usually say, hey, wait a minute, how much voltage am I getting from you guys on average? It's 0. Most of the engineers know that. All right. So which means that the voltage is what drives current. So on average, I'm not getting any current from the power company. So the question is, what am I paying for? All right. At that point, they end up passing the phone around. And that's the fun thing. Because all of a sudden, it's a good question. But what the hell am I paying for? Because on average, literally, I'm not getting anything from the power company. Eventually, they find someone who knows how to answer the question. That's actually kind of cute. I'm not paying for voltage. I'm not paying for current. I'm paying for power. That's the reason why it's called power company. All right. Some genius must have figured this out. More than likely, some physicists were pulling this prank on the power companies for a long time. All of a sudden, they go, oh, they sell power. They don't sell current. They don't sell voltage. All right, they're selling power. So what's the meaning of it? Guys, the current and power do the same thing. All right. So the voltage is what drives current. So voltage goes up, the current goes up. Voltage goes down, the current goes down. Voltage goes up, the current goes up. On average, you get 0 voltage. On average, you get 0 current. But on average, you don't get 0 power. All right. So what's the meaning of that? You get a lot of power from the power company, despite the fact that on average, the amount of current that we get is 0. The amount of voltage that we get is 0. So in order to deal with jerks like me, they decided to come up with an interesting mathematical system, which I really like. All right, guys, here's your current. Here's the maximum value of the current, and here's the maximum value of the voltage, right? So what's happening is the current is going up and down. On average, we're getting 0 amount of current. The voltage is going up and down. On average, we're getting 0 amount of electromotive force or voltage, whatever. All right. All right, so this is the current amplitude, this is the voltage amplitude, but notice that both of them are going up and down as a sine wave. All right. So sine of omega t times sine of omega t is going to be the sine of the square of omega t. So when you put it that way, the power is going to look a little bit different. So now this becomes the maximum amplitude of power that we end up getting. All right. And then you have the square of the sine wave that we got. Now the square of the sine wave now looks like this. Okay, notice that nothing is below 0. All right, so power is going to vary between a 0 amount of power and a maximum amount of power. And then the power company, those guys are nice. Obviously, are you going to pay for the maximum amount of power, or are you going to pay for the 0 amount of power? Okay, so this is not fair because these people are giving us power, so they're going to say, hey, we're not going to charge you at the minimum. And they want to be fair. They're going to say, we're not going to charge you at the maximum either. Why don't we compromise, and why don't you pay us for the average power? Notice that the average power is going to be half the maximum power in this case. So this is your maximum power right here. and half of it becomes the average power. All right, they charge us for the average power. Okay, so they're being fair. And so they usually, if you can find someone who knows what's going on, it's very rare. You have to talk to 10 engineers and one of them will go, oh, I know what you're up to. They know immediately that you're a physicist at that point. And they also know that it's a prank at that point. All right, but they tend to be fairly patient. You're paying for the average power. Another thing that they do in order to avoid these kind of pranks, they will tell you that they know that you're a consumer and you're consuming in reality current. And the average current that you're consuming is 0. But because they're charging for the average power, okay, they have to give you some kind of an interpretation as to how much current you're paying for. Okay, that's another thing that I would just pump for, because I would say, yeah, you're charging for power, but how much current am I getting on average? And you can confuse the hell out at that point. And it's fun. It's fun. These guys are professionals. And so these guys, clever geniuses, came up with another term that you can use for average, which is you can take this term, which is the average. So this is the maximum that you have. So they don't want us to pay for the maximum amount of current that we are using. They want us to pay for a non-zero average of the current that we're paying for. This is known as the RMS value. All right, so let's talk about the RMS value. All right, so RMS values, you have 1 divided by 2 can be expressed in terms of 1 divided by square root of 2 times 1 divided by square root of 2. So notice that we have 1 over 2 in front of average power. So we can express that 1 over 2 in front of average power in terms of 1 over square root of 2. So one of the square root of 2 is 1 over square root of 2 is going to go in front of the maximum current. The other is going to go in front of the maximum electromotive force. So this maximum current value divided by square root of 2 is known as root mean square average. This is known as the RMS value. This is a non-zero average of anything that is 0 average. All right, so they would tell you that, hey, you're not paying for the true average, you're paying for the root mean square average of the current value, which is going to be non-zero in essence. All right, case in point. The voltage that we get from the socket is 120 volts. All right, this is the amount of voltage that the power company says we're getting. This is the root mean square average, RMS average of the voltage that we're getting. In reality, the maximum voltage that they're supplying us is going to be 170. It's 170 volts. All right, so that's how it is done. So they're not charging us for 170. They're charging us for RMS, which is the non-zero average. Okay, so the terminology is important because it comes up from time to time. RMS values. All right, so what's the relationship between maximum electromotive force and the frequency of the spin? All right, so you spin the wire. Okay, spinning the wire is going to change the flux. To change the flux is what generates electromotive force. All right. So by spinning the flux, by spinning the coil, you're changing the size of the area exposed to the magnetic field. In turn, that's what causes the flux. So you're just varying the angle per second. All right, so the relationship between the maximum electromotive force and the frequency of the spin is direct. All right, so faster you spin this thing, larger the electromotive force is going to be. All right, so the maximum electromotive force that you can have, this is this term, depends on the number of turns, depends on the area, size of the area of the loop, depends on the strength of the magnetic field intercepted by this loop, and then also it depends on how fast you will spin this omega. So it's going to depend on the angular frequency. All right, so angular frequency is, this is your linear frequency times 2 pi. 60 hertz is going to be the linear frequency. We have more. All right, so the root mean value averages is a non-zero average that you're looking at. So maximum value divided by square root of 2 in both cases. All right, so average power is going to be half the maximum value of the power that comes out of that. All right, so this is known as the motional electromotive force. All right, so this is the electromotive force generated by the motion of a conducting rod, metal rod, inside a magnetic field. All right, so let's study this. Magnetic field is pointing into the page in this case, and the rod is driven in this direction, perpendicular to the direction of the magnetic field. So what's happening inside the rod is, notice that the top of the metal rod, the conducting rod, becomes positively charged, the bottom becomes negatively charged. All right, so all of a sudden there's charge separation. Top region is positively charged, the bottom region is negatively charged. So when there's a charge separation between these two regions, which are separated through a certain distance, there's going to be a voltage difference, or electromotive force. So the question is, what causes the charge separation inside the metal or conducting rod? What causes the charge separation is the same as the right-hand rule number 1. Imagine that there's a positive charge here, and the charge is moving across the magnetic field in this direction, right? So what happens? It's going to experience the force in the opposite direction. So the positive charge will experience the force in the opposite direction. Negative charge will experience the force in the downward direction. As a result, the top is going to become positive charge, the bottom is going to become negative charge. All right, so here's our positive charge inside the conducting metal or conducting rod. So magnetic field is pointing into the page. Positive charge is moving, forced to move in this direction. So use the right-hand rule. Fingers are going into the page. It's pointing in the direction of the velocity vector. The palm points in the upward direction. So positive charges will get pulled in the upward direction. The negative charges will get pulled down in the downward direction. So positive charges will experience a magnetic force in the upward direction. The negative charges will experience a magnetic force in the downward direction. So the charges are moving in the forward direction. Magnetic field is into the page. Positive charges will experience a force in the upward direction. As a result, they will pull towards the top. Negative charges will experience a force in the downward direction, so they will pull towards the bottom. Top becomes positive charge, bottom becomes negative charge. Now you have the electric field pointing from positive charge region towards the negative charge region through this separation distance L, which means that there's going to be a voltage difference between the top and the bottom. So what that means is this conducting rod now is acting like a battery. It turns into a battery because there's going to be a voltage difference between the top and the bottom. All right, so I'm going to skip the algebra. I'm not interested in the algebra. Okay, so the motion of this rod, which has the length L, within this magnetic field, all right, at this speed, is going to cause an electromotive force within the rod, which means that the rod itself is going to act like a battery. In essence. All right, so this is the formula. I like this interpretation of the formula. So we're going to be interested in the component of the velocity vector, which is going to be perpendicular to the magnetic field. All right, so this is the direction of the speed, which is perpendicular to the direction of the magnetic field of this rod, which has a length L. All right, so faster this goes, and more perpendicular this is to the magnetic field, the larger will be the electromotive force. If you hook a circuit onto this rod, there's going to be current inside the circuit because the electromotive force is what drives the current inside the circuit in essence. And then we'll get started.
I've got to tell you, a few weeks ago, I saw the White's metal detector ad on TV. In no time at all, my local dealer had me out treasure hunting. I was finding the good stuff my first day. And the best part? You can see what's in the ground before you dig it up.
Your treasure hunting adventure can start right now. Call for your free catalog.
My wife said I needed a healthy hobby. She's proud of the weight I've lost, and really proud of this.
Call now.
All right, so the metal detectors, how do they work? Okay, so induction. Okay, guys, we got a little bit of a lecture left from the previous chapter, so let's finish this up. The induction is what we were dealing with. Okay, notice that you got two coils. One of them is the primary coil. The second one is the secondary coil. Primary coil is attached to an AC generator, the alternating current generator. Secondary coil is not attached to anything. There's a voltmeter, so it's going to read the voltage across it. All right, so alternating current generator is going to generate an AC current. So the current is going to go this way and that way, this way and that way. So it's going to keep changing direction, right? So the current is going to keep changing direction as well as value. So you know that the current is what produces magnetism. So when the current goes this way, the magnetic field is going to go in that direction. And when the current reverses direction, the magnetic field is going to also reverse direction. When the strength of the current is increasing, the strength of the magnetic field is going to increase. When the strength of the current is diminishing, the strength of the magnetic field is also going to diminish. So this AC current here is going to cause a variable magnetic field. Magnetic field is going to point this way and that way, this way and that way as its strength is changing. Notice that the magnetic field generated by the primary coil is going to be intercepted by the secondary coil. If you vary the strength of the magnetic field intercepted by the secondary coil, what's going to happen? It's going to cause an alternating current in the secondary coil, right? So the alternating current within the primary coil is going to cause a variable magnetic field. And when you intercept that variable magnetic field by the secondary coil, within the secondary coil, there's also going to be alternating current. Except the alternating current.
The most common and thorough technique is the minesweeper. It's also the most dangerous.
All right, so before we get back to that one, notice that we're able to induce current on the secondary. All right, so this sort of setup is known as inductance. We're able to induce current on the secondary. All right, and this phenomenon is known as mutual induction. So the alternating current within this primary coil is going to be able to generate an alternating current within the secondary coil by varying the magnetic flux. Metal detectors, how do they work? All right, so here's a simple setup. Just study this. I'm going to give you guys like 15 to 20 seconds. And then I'm going to run through the setup. Now this one is a simple metal detector. You got the transmitting coil, the primary coil, and you have the secondary coil, which is known as the receiving coil. Both of them are set up 90 degrees to each other. So the question is why? Why set them up in this fashion? Okay, so the transmitting coil is going to have alternating current running through it. So the current itself is going to generate a magnetic field. The current, notice that it's got two directions, so which means that the current is alternating current, which means that it keeps changing direction. Not only does it change direction, also obviously the value of the current is changing. So the current goes this way, the magnetic field is going to go one direction, and then you reverse the direction of the current. It's going to reverse the value as well as the direction of the magnetic field. All right, so in this case, according to this schematic, we got buried gold coins in the ground. So which means that they're made up of metal, so they will be neutral, which means that they got conduction electrons within them. And these electrons are free to move, right? So what happens when you start to vary the strength of the magnetic field, intercepted by these gold coins? So that's the cross-sectional area. So within this area, if you keep varying the strength of the magnetic field, what happens? It's going to set up eddy currents within the gold coins. Eddy currents in turn will generate their own magnetic field. So their magnetic field generated by the eddy currents within the gold coins is going to get intercepted by the receiving coil. Okay, so if the strength of the magnetic field generated by the gold coins, if it varies within this, within the cross-sectional area of this receiving coil, it's going to generate a current within the secondary coil, right? If there's current within the secondary coil, that's when you will hear the beeping sound. All right, so why is it that this is set up at 90 degrees to the transmitting coil? Because if it is set up 90 degrees to the transmitting coil, none of the magnetic field generated by the transmitting coil is going to get intercepted by the secondary coil. All right, so you don't want the secondary coil to intercept the magnetic field generated by the primary coil, because if it starts to intercept the magnetic field generated by the primary coil, any variation of the strength of the magnetic field within the receiving coil is going to generate current, so you don't want to do that. All right, so in case there's a test question, and sometimes I like to ask this on the test, that this would be a good conceptual question on the conceptual part of the test. All right, so the metal detectors usually work on this principle. Once again, you have a variable alternating current. Alternating current is going to generate a variable magnetic field. Magnetic field intercepted by the area of these coins is going to cause eddy currents within the coins. Eddy currents in turn will generate their own magnetic field. When that magnetic field gets intercepted by the receiving coil, if the strength of the magnetic field is changing, obviously it's going to induce a current in the secondary coil, and induced current is going to cause that beeping sound that you hear. All right, so it's based on the idea of mutual induction. So once again, speaking of the mutual induction, the alternating current within the primary coil is going to cause a change in magnetic field, right? And the change in magnetic field intercepted by the secondary coil is going to cause an alternating current within the secondary coil. So we're going to be able to induce current in the secondary coil using it that way. All right, so mathematically, it looks like this. All right, so here's the inductance that we're going to be talking about. All right, I'm not going to put too much emphasis on the mathematics of it because this tends to be rather technical for most of you guys. Most of you guys are biological science majors, but I want you to kind of get the idea so you can actually answer some of the conceptual questions. So what do we know? We know that the current within the primary, which is this, will cause the flux within the secondary, which means that it's going to generate the current within the primary is going to generate enough magnetism, which is going to get intercepted by the coil in the secondary. All right, so what this means is the flux, the amount of magnetic field intercepted by the secondary coil, is going to depend on the current in the primary coil. All right, so that's the meaning. The flux of the secondary, which is the amount of magnetic field intercepted by the secondary coil, is going to depend on the current within the primary. Okay, so we will just add on to it. Flux on the secondary is going to depend on the current within the primary, but we're talking about the flux on the secondary of one single loop. If you have multiple loops, obviously, which means that the effect of the flux is going to get magnified, right? If you have one single loop, this is the flux within the secondary loop. If you have multiple loops, this is the flux within the secondary multiple loops that we're looking at. All right, so the amount of flux in the secondary of every single turn is going to depend on the current within the primary. So which means that it's going to be proportional to it. So we end up using a proportionality constant, which is known as mutual inductance. Okay, so we turn this into an equation. So the mutual inductance is going to tell us how much of this current value within the primary, the current within the primary, is going to cause a flux within the secondary. All right, so the mutual inductance is going to tell us how much the effective current within the primary is going to enhance the flux within the secondary that we're looking at. All right, so in essence, what we're doing is we keep changing the current within the primary. Is going to cause a magnetic field within the primary. The magnetic field within the primary is going to get intercepted by the secondary. So any variation of the strength of the magnetic field in the secondary is going to induce a current in the secondary. All right, so that's the stuff that we've been discussing. All right, if you increase the strength of the current within the primary, it's going to induce a current within the secondary, and the current in the secondary is going to be moving in the opposite direction in this case. All right, so current in the primary is going to induce a flux in the secondary. Effects of flux can become magnified by increasing the number of turns in the secondary. And then we turn this into an equation by multiplying by a proportionality constant known as the mutual inductance. So the mutual inductance is going to tell us how much the effective current within the primary is going to be enhanced in terms of the amount of flux that it's going to be able to generate through these number of turns of the secondary that we're looking at. All right, so the mutual inductance is going to have the units of H. H stands for Henry. All right, let's talk about Henry briefly, so it's not as technical as it needs to be. Okay, so the inductance concept is something that Faraday came up with, obviously. And in honor of Faraday, capacitance as the units of Faraday. All right, so Henry, the Faraday's name is being used up already, at least in one of the physics concepts, which happens to be capacitance, right? Okay, Henry is a guy from New York State. Okay, this guy was actually a high school physics teacher. I think this is the 1800 or something. And then he was the first person who was able to build an electromagnet. All right, and because of his invention, in his honor, inductance as the units of Henry. High school physics teacher from Rochester, New York. All right, so let's get back to the topic again. All right, so what do we know? The current within the primary is going to cause a flux within the secondary, right? So what happens if we vary the current value in the primary? If you vary the current value within the primary, it's going to change the flux within the secondary, right? And all of a sudden you go from here to there. If I change the current value within the primary by changing its direction as well as its value, what I'm doing is I'm actually changing the flux within the secondary. And you know from Faraday's law that changing flux within the secondary, changing flux is what causes the electromotive force. This is what caused the voltage in essence. Okay, so we got the negative sign. We got the negative sign because of the Lenz's law that we discussed. So the current is going to move in a direction that's going to oppose any change in flux in essence. All right, so let's just back up one more time. All right, so the flux within the secondary, which is this, is going to be caused by the current within the primary. All right, so you can increase the effects of the flux by increasing the number of turns, right? And then you turn this into an equation by multiplying by a proportionality constant known as the mutual inductance. And this simply tells you how much the current is going to be able to influence the amount of flux that you're going to be able to generate. How much the current within the primary is going to be able to influence the amount of flux that we will be able to generate on the secondary. That's what it means. We know that if you vary the amount of current within the primary, so the invariation of the current is going to vary the strength of the magnetic field. So which means that the magnetic field intercepted by the secondary, the value of the magnetic field is going to keep changing. So what this means is if you vary the current within the primary, changing current within the primary is going to change the flux within the secondary. And any variation within the flux within the secondary is going to cause an electromotive force in the secondary, which means that it's going to generate current within the secondary. So that's the meaning of this chapter. All right, so that's exactly what this means. And then you have the negative sign indicating that the electromotive force is going to point in a direction that's going to oppose any change in flux. So here's the change in flux. You put a negative sign indicating that the electromotive force is going to act on a direction that's going to oppose any change of flux within the area of the coil that we're looking at. Okay, that was mutual induction. Now there's also something called self-induction. Okay, so self-induction is the following. It's the same concept, except this time we have only one single coil. All right, so that's the solenoid that you're looking at. We got a single solenoid here. And then we have current in this case, and then the current is going to create the magnetic field. The magnetic field generated by current, notice that it's also being intercepted by the area of this loop, right? All right, so the current generated by this coil is also intercepted by the area of the loop itself. So if you vary the value of the current, as well as the direction of that current, you will end up varying the strength of the magnetic field intercepted by the coil. As a result, this variation within the strength of the magnetic field is going to induce a current in the opposite direction of the original current. So it's going to end up changing the total value of the current within the inductor in essence. All right, so that's known as self-induction. All right, so the idea of self-induction is the same as the mutual induction, except now you have just one single coil. All right, the single coil that we have is a solenoid. So the amount of flux, the amount of magnetic field intercepted by this coil is going to depend on the current value, right? A single coil, the amount of flux of a single coil is going to depend on the current within that coil. And obviously, if you have multiple coils, that's multiple turns, or the coils in this case, like a solenoid, you can increase the intensity of the flux by multiplying everything by n. All right, so the amount of flux intercepted by the total number of coils, the turns that you're looking at, depends on the value of the current. So which means that it's going to be proportional to the value of the current that we're looking at. All right, turn this into a proportionality. This is a proportionality turned into an equation by multiplying with a proportionality constant. In this case, it's this L. L means induction. Only in the books you see the term self-induction, but it's just an induction. That's it. Once again, it's going to have the same units of H. H is going to be Henry. So if you vary the current, the value of the current is what is the direction of the current. You're going to end up changing the strength of the magnetic field intercepted by this area, which means that you're changing the flux, right? So it's going to end up causing an electromotive force. All right, this is otherwise known as the back EMF, electromotive force. So this electromotive force is going to act in a direction that's going to oppose any change of flux within this, which means that if your current value is increasing in this direction, the induced current is going to be opposing that change. So which means that the circuit is going to create a current opposing it in the opposite direction. So it's going to start to reduce the value of this current in essence. And if you're reducing the value of the current is going to act in a direction which is going to oppose that change. And in a sense that these inductors will act like variable resistors, whatever that means to you guys. We'll find out. Okay, so these inductance values, mutual inductance or self-inductance. Okay, what does it depend on in essence? All right, so the inductance is going to depend on geometry. So like capacitance values, the inductance value is also going to depend on geometry. Okay, so let me just take you through the logic. All right, so here's the general formula that we were looking at. So the current is going to induce flux through each and every single turn. And how much flux it's going to be able to induce is going to be this L. So this L is the inductance. So this is going to tell us how much the value of this current is going to get enhanced through the loop of the wire that we're looking at, or coil in this case. All right, so solve for L. And then so we isolate L on the left-hand side. See the number of turns that we got. All right, so the current is going to be current within the wire. So the flux that we're looking at, flux by definition is the amount of magnetic field intercepted by the area of the loop. And in this case, the magnetic field that we're looking at, so that's the amount of magnetic field which is going to be intercepted by the area of the loop. And the loop that we're looking at, this is a solenoid. All right. So this is the amount of magnetic field which is going to be intercepted by the loop. So this is the magnetic field generated by a solenoid. This is the formula that we came up with previous week. So this is the amount of magnetic field generated by a solenoid. So you do a back substitution in that formula. When you do a back substitution, what happens is, so this is the flux. All right, so it's going to be this number times A is going to go there. All right, so this whole expression becomes this expression. Notice that the current values will cancel out, so the current is not going to matter. At the end, this is the expression, mathematical expression that we come up with. So inductance is just what happens is going to depend on the area of the loop that you're looking at. N represents the number of turns that we have, and lowercase n represents the number of turns per unit length that we're looking at. So n and capital N and lowercase n are related in this fashion. All right, so the number of turns per unit length is going to be lowercase n. All right, so the number of turns can be expressed in terms of the number of turns per unit length times length. So you can actually do a back substitution. You can take this and substitute right there. It's going to give you this final result. All right, so the final result that we're going to be looking at is going to be the number of turns per unit length squared times length times the cross-sectional area. So the inductance, in essence, is going to depend on geometry. That's it. Inductance is going to depend on geometry. All right, so capital N represents the number of turns. A represents the cross-sectional area. L represents the length. Number of turns per unit length is going to be lowercase n. This is your A. And that's it. All right, so it only depends on geometry. All right, so that's the detail that I want you guys to remember. Don't worry about the derivation so much, but just understand the detail. Inductance depends on geometry. Okay, so the self-inductance increases under which of the conditions? All right, let's take a look at the final formula. All right, so on number of turns per unit length. Okay, this will require a little bit of a justification. All right, so by increasing the number of turns, you can certainly increase the inductance. Okay, I need to stop right at this point. All right, so by increasing the number of turns, you can definitely increase inductance. This is the same as number of turns per unit length. If you increase the per unit length, it's going to actually reduce inductance. All right, so increasing the length is actually going to reduce inductance. Not the best answer in reality. All right, so the number of coils, number of turns increased should be the correct answer for this one. All right, let me go back to the justification for that one. Okay, if you're looking at this formula, you will say, oh, it's if you increase the number of turns, it's going to increase inductance, right? But you got to remember that this lowercase n is the number of turns per unit length. All right, so if you do a back substitution here, what do you have? So you have number of turns, capital N times capital N, so it's going to be n squared divided by L in essence. That's what you end up getting here. All right, so which means that if you increase the length, the inductance is going to go down. But if you increase the number of turns, the inductance is going to go up. So if you increase the number of turns per unit length, is not the best answer. D is the best answer for this.
An electric current in any circuit creates a magnetic field which, whenever it changes, induces a current in the same circuit that opposes the change. This phenomenon is called self-induction. The effect of self-induction is larger in a coil of many turns, called a solenoid, precisely because it loops many times around the changing flux. That's why a solenoid is used as a symbol of self-inductance in an electric circuit, where an inductor may be an element like a resistor or capacitor.
Current increasing in an inductor causes an opposing electromotive force, according to Faraday's law. And since the flux is proportional to the current that creates it, that electromotive force is equal to minus a constant L times the rate of change of current. L is called the inductance of the circuit element. An inductor opposes and slows down the buildup of current in a circuit, while a resistor may cause the current to decay by dissipating energy.
All right, let's go through it one more time.
An electric current in any circuit creates a magnetic field which, whenever it changes, induces a current in the same circuit.
All right, so let's go through it one more time. All right, so the current generates magnetism. And notice that the magnetic field that it generates is going to become intercepted by the area of the loop, right? All right, so if you vary the strength of the magnetic field intercepted by this loop, it's going to induce a current that's going to oppose that change.
Field, which, whenever it changes, induces a current in the same circuit that opposes the change. This phenomenon is called self-induction. The effect of self-induction is larger in a coil of many turns, called a solenoid, precisely because it loops many times around the changing flux. That's why a solenoid is used as a symbol of self-inductance in an electric circuit, where an inductor may be an element like a resistor or capacitor.
Current increasing in an inductor causes an opposing electromotive force, according to Faraday's law.
So if you are increasing the current value within an inductor, it's going to induce a current opposing that change.
And since the flux is proportional to the current that creates it, that electromotive force is equal to minus a constant L times the rate of change of current. L is called the inductance of the circuit element. An inductor opposes and slows down the buildup of current in a circuit.
Okay, so inductor is going to act like a variable resistor because it's going to oppose any buildup of current, as well as it's going to oppose any decay of current.
While a resistor may cause the current to decay by dissipating energy.
All right, so that's what an inductor does in a circuit. Case in point, look, I'm increasing the current value in this direction. As soon as I increase the current value, what happens? The induced electromotive force is going to be opposing that change. All right, which means that it's going to generate current in the opposite direction in order to oppose that increase in value of the current. If I'm reducing the value of the current, this time the electromotive force is going to act in a direction that's going to actually oppose that change in the current value. All right, so it's going to oppose I can't find the right words at this point. It's going to oppose any decreasing value of the current. All right, so that's what it does. If the charge value is increasing, it's going to oppose that increase in charge value. If the charge value is decreasing, it's going to oppose a decrease in the charge value. If the current is increasing, it's going to oppose that increase. If the current is decreasing, it's going to oppose that decrease. And that's what an inductor does. Okay, so this is known as our L circuits. Okay, so you have a resistor and an inductor within the circuit. The current is building up in this direction. So if you're building up the current, the inductor is going to actually oppose that buildup. If you're diminishing the current, once again, the inductor is going to oppose that diminishing value of the current in essence. All right, so we got a switch here. You got the battery. All right, so you put the switch on, so the current is going to build up. As the current is building up, what's going to happen is the voltage across is just going to increase, voltage across the inductor is going to increase, trying to reduce that buildup of the current value. If you throw the switch off, this time the current value is going to diminish, and then the voltage within the inductor is going to act in a direction that's going to actually reduce that change in voltage. All right, so if the current is building up, notice that the voltage is going to increase through the inductor. If the current is going down, this time the voltage is going to move in a direction that's going to oppose that change. All right, so the RL circuits, in this case, for the switch on, the voltage is increasing across the resistor. So the inductor is going to induce electromotive force that's going to oppose that change. All right, so when the current is building up across the resistor, that's the meaning of it. So the current is building up, the charge is building up. And then you throw the switch off. This time, the current is actually diminishing across the, all right, let's say it correctly. I'm just getting myself confused here. All right, so the voltage across, okay, so the voltage across the resistor is building up, which means that the voltage across the inductor is trying to oppose that change. As this is building up, all of a sudden the voltage opposes, there's voltage in the opposite direction, which is opposing it. I think that's what it means. Okay, let me just set up the mathematics for it. All right, the details of this is not that important. So the current value is building up. All right, so the current value is building up as soon as you close the circuit. All right, so the two formulas that we're going to be looking at, across the inductor, this represents that the current is going to start to build up to its maximum value. All right, so IO in this case is going to represent the maximum amount of current that you can have inside the inductor. Okay, so this represents the current value just building up inside the inductor. Okay, I don't know why there's an R there. That caused a bit of a confusion here. Okay, so this tells you that the current value is going to slowly build up across the inductor within the RL circuits. All right, so this is the maximum value that it's going to build up to. And notice that in the exponent of this exponential that we're looking at, the power of the exponential exponent. And you have R divided by L, or L divided by R if you're looking at it from that perspective. That's going to be our time constant. This is known as the inductive time constant. All right, so the inductive time constant is going to tell you how fast the current is going to build up. Okay, so that's the meaning of it. How fast the current is going to build up. We've seen this concept when we were dealing with the capacitors. Remember, there was a capacitive time constant. This is the same concept, except this is known as the inductive time constant. It's going to tell you how fast the current is going to build up. All right, so the larger the capacitance value is, the longer it's going to take. All right, so the larger the capacitance value is, the longer it's going to take for the current to go up. Larger the resistance is, slower it's going to take. All right, so this time the current is going to be decaying. Obviously, the battery is taken out of the system. So this tells you how fast the current is going to decay. So this is the formula that we will get to use for that one. So the current is going to decay from its maximum value. Okay, so mathematically, I'm not too keen on giving you guys a lot of problems regarding this. Okay, I want to take a look at problem number 3, so you guys can at least see how the concept takes shape. All right, so we have a solenoid. It's got an inductance value. The inductance is expressed in terms of millihenries. It's got a resistance value, so it's going to be expressed in terms of ohms. All right, so it's connected to a battery, and obviously, which means the current is going to build up. So the question is, how long will it take for the current to reach 1/2 of its maximum value? That's what we're looking at for a problem like this. How long would it take for it to reach 1/2 of its maximum value? So here's the inductance, here's the resistance. The time is what we're looking for. So we are interested in the amount of time it takes for it to reach 1/2 of its maximum value. All right, milli is going to 10 to minus 3, expressed in terms of Henry. Everything else is fine. Everything else has the proper units. All right, so we will hook this up onto the battery, and the current is going to build up, obviously, through the RL circuit. So we're interested in the amount of time it takes for it to reach 1/2 of its value. I think it's going to be here, honestly. All right. So the stuff that we're interested in is t here, lowercase t. It's going to give us the time. All right, this tau L, this is the Greek letter tau. That's the inductive time constant we're looking at. It's going to be L divided by R, so that's fine. All right, so I'm just rewriting this so that we have the resistance and inductance values. All right, the only thing we are looking for is the time, lowercase t. All right, so we're also given the value of, all right, so you want to reach 1/2 the maximum value. So this is going to be 0.5. All right, so I'm just going to do my algebra. I'm going to isolate the t term on the left-hand side. Notice that the exponent is a negative value. So what I'm going to do is I'm going to invert both sides of the equation. All right, so there's a negative sign, and because I end up moving this here, and I end up moving that there, there's no negative sign in reality. Or is there a negative sign? Why? Oh, okay, put a negative sign there. Oh, because I'm moving things around. That's weird. Anyway, so invert both sides and take the natural log of both sides. And then we end up coming up with this expression. Natural log of 1 is going to be 0, so that drops out. Get rid of L. And that's it. And then plug the numbers in, everything should work out. Okay, so we got numbers for everything else, so that's it. All right, so I don't think I plugged the numbers in, but. So what's mutual induction? What's self-induction? What determines the value of inductance? How does self-induction actively oppose any variation within the current? What is an inductive time constant? Okay, so those are the basic questions. Okay, so why is AC better than DC in transmitting electrical power in long distances? What purpose does a transformer serve? Compare the variation in flux within the primary and the secondary coils and state if they could have the same, if they could have a value that's different from each other. So I have to explain them. So what's the purpose of the iron core? Okay, so these are the ones that we've already done in the previous lecture. Okay, guys, what's mutual induction? What is the mutual induction? Let me just hit.
When there are two coils, and the primary coil induces current in the secondary coil by varying magnetic flux.
Okay, very good. Give yourself 10 points for that. So the mutual induction is how much the current within the primary, changing current within the primary, is going to induce flux. It's going to vary the flux within the secondary, right? In essence. How much is going to vary the current within the secondary coil, which has this number of turns, right? I'm writing like a little kid. That's it. All right, so give yourself 10 points for that one. What is self-induction? Self-induction is the same concept. How much the current within the coil, or the changing current within the coil, is going to change the flux inside the same coil. A coil that has God knows how many number of turns. In turn, that's going to set up an electromotive force, opposing that change. All right, so what determines the value of inductance, L or M? I don't care which one you're using. So it's going to be geometry, obviously. So area is important. What else is important? The number of turns is important. I kind of need to remember that this is the formula that we will get to use. There's one constant. Okay, so what else do we have? Okay, I think this is it, right? So number of turns squared divided by L, the length, times the constant times the area. So important stuff is the geometry, L, number of turns, and the area. All right, so we got the number of turns per unit length, and then the area. Geometry is important. Geometry, okay. How does self-induction actively oppose any variation within current? Okay, so when in the case of self-induction, all right, so it's okay. So when we have the self-induction, all right, so the current itself, if you're varying the current within any solenoid, okay, so what does it do? It's gonna create an electromotive force, and that's gonna oppose any change within the value of the current. So which means that it's gonna set up an electromotive force. It's gonna oppose any change in the value of the current. So it's gonna generate a current that's gonna oppose any value of the original current. That's what it means. Okay, so what's an inductive time constant? Inductive time constant is, it's going to tell you how fast the current is going to build up within an RL circuit that we're looking at. So this circuit is going to have a resistor, and it's also going to have an inductor. And then we hook it up to a battery, and then the current value is building up in this case. All right. So larger the inductance is, the faster it's going to build up. That's weird. Hold on. That can't be true. Okay. All right. So the equation is it's supposed to look like this. All right. Okay. Hold on. Larger the resistance is, slower it's going to build up. Larger the inductance is, the faster it's going to build up. That doesn't make sense. Okay. All right. Inductor is going to oppose any variation of the current value, so which means that there has to be an inverse relationship. All right, TL. Okay, guys, let's take a look at the formula. This looks weird. Okay, then that makes sense. Okay, so larger the inductance value is, the longer it's going to take. Okay, that's fine now. Okay, so larger the inductance is, the longer it's going to take for it to charge up. All right, so this represents the time it takes for it to build up its maximum value, or time it takes for it to decay from its maximum value.